Well, my days of not taking you seriously are certainly coming to a middle.
Imagine that you have set up two Cartesian coordinate systems. One, the blue one, uses coordinates x and y. The green one uses coordinates x bar and y bar. Once again, I mustn't think that xy is more fundamental than x bar y bar is, because I could either turn my head or turn the piece of paper, and now x bar is horizontal and not xy. A circle is the set of all points that lie a common distance from a given point, the center. If I draw a circle in the xy coordinates that has x squared plus y squared equals 1, I'll get a circle centered at the origin, radius 1. Distances are left invariant with respect to rotations, so even though the x bar and y bar axes are tilted with respect to x and y, it still must be x bar squared plus y bar squared equals 1. One of these groups will say, we have a circle. The other one will say, yes, we do. Its radius is 1. The first group will say, not only that, the center's at the origin. The other group will say, yes, it is. So we're in complete agreement in terms of all of the circle information. Except that the agreement isn't exactly what you think it is. The unbarred system will say, yes, the highest point on the circle is this red spot. According to the barred coordinates, though, that isn't true. According to the barred coordinates, the yellow spot is the highest spot on the graph. If I ask who's right, this is a meaningless question. What I can say is that both coordinate systems agree that each point as observed on their circle is a point on the other person's circle, and vice versa. But if I start talking about highest spots or vertexes of parabolas or vertices of hyperbolas and stuff, I'm not necessarily going to get agreement between the two different coordinate systems. In the previous situation, we're talking about rotations. Rotations leave distances invariant when you go from one Cartesian coordinate system to another. In our new situation, instead of just having Cartesian coordinates, we have inertial reference frames instead. Instead of this kind of quantity being invariant with respect to our new and as of yet unnamed transformations, the quantity that is invariant is the space-time interval. X squared plus y squared equals 1 is the set of all points whose distance squared from the origin is 1. Both the barred and the unbarred coordinate system have the same kind of formula for this. One is x squared plus y squared equals 1. The other is x bar squared plus y bar squared equals 1. Both represent the same circle, although the location of a given point depends on your point of view. In our new situation, we have the space-time interval instead. if I look at all of the points whose space-time interval from the origin to the point in question is 1, working in one space variable and one time variable, I find out that negative t squared plus x squared has to be 1. Of course, since the space-time interval could be positive or negative, I really should also look at the case where negative t squared plus x squared is negative 1 also. Let's look at one of these. Because of the invariance of the space-time interval, the set of points that obey this equation of space-time are the same points of space-time that obey this equation, although just with the circle, their particular location may be a little bit stranger than you would otherwise think. So let's draw this invariant hyperbola in the x bar t bar coordinate system. I'm going to think of point P as being the origin, which parenthetically is also the origin of the unbarred system. I'm going to imagine an individual initially located at t bar equals 0, x bar equals 0. I'll call that point P. I'll think about the location of point Q so that t bar is 1, x bar is still 0. This corresponds to a situation of someone sitting at the origin of the barred coordinate system at rest and allowing 1 unit of time to pass. So from here to here, 1 unit of time, as measured in the barred system, has passed. Also, both points P and Q are on the t-bar axis, which we have previously identified in the space-time diagram of the unbarred coordinates. Because of the invariance, t squared minus x squared equal 1 is the same set of points of space-time as t bar squared minus x bar squared equals 1. On the other hand, let's draw in the t-bar axis as well. We've previously seen that the t-bar axis in the unbarred coordinates can be expressed as x equal vt. I can find the upper intersection of the invariant hyperbola with the t-bar axis and call it r. This is a point that is on the invariant hyperbola and is also on this t-bar axis, but obviously there's a spot that is on the t-bar axis and on the hyperbola, so point R actually is the same as point Q. If I can figure out the unbarred coordinates of point R, I'll know what the coordinates of point Q are according to the unbarred system. If I make use of the fact that my point is both on the hyperbola and on the t-bar axis, if I combine those two equations, it's not very hard to solve for t. I'm looking at the positive t here. T is 1 over square root 1 minus v squared, and since x is v times that, x is v over radical 1 minus v squared. This is very interesting. Between events P and events Q, the barred system measures 1 unit of time as having elapsed. However, the unbarred system measures that amount of time as having elapsed. Hey, Matt. According to people in the barred coordinate system, 1 unit of time has passed, while those in the unbarred system say 1 over radical 1 minus v squared units of time have passed. That second quantity is bigger than the first quantity is. The unbarred coordinate system is going to say that more time has passed than the people in the barred system are saying. The people in the unbarred system are going to claim that the clocks of the barred system are running slow. The people of the unbarred system are going to claim that the clocks in the barred system are running slow by a factor, this factor. It's worth mentioning that we're using units where the speed of light is 1. If I wanted to drop back to ordinary units, I would have to say that v is the fraction of the speed related to the speed of light. If I wanted to write this in ordinary meter kilogram second units, I would write it that way. This is called time dilation. This utterly destroys the idea of absolute time. We already knew it was in trouble because of the simultaneity business, but now even the scale of time is different depending on which coordinate system you're using to do the measuring. We'll look into some detailed calculations of this at another time. What about space? In the barred coordinate system, I'm going to let P be the origin and Q be the point where T bar is 0 and X bar is 1. These 2 points represent things that happen at the same time, so the space-time interval between them is just the square of the distance between them as measured in the barred system. The distance squared is 1. Also, P is the origin and Q is on the X bar axis, which we have also located in the space-time diagram of unbarred coordinates. If I think about X bar squared minus T bar squared equals 1, this is part of my whole invariant hyperbola idea. Point Q is on the invariant hyperbola. In fact, it's a vertex of it. On the other hand, point Q is on the X bar axis, which we know how to draw in the space-time diagram of the unbarred coordinates. Invariant hyperbola is x squared minus t squared equals 1, and the X bar axis had that funny symmetry. The T bar axis was x equals vt, the X bar axis is t equal vx. The intersection of these two objects, the X bar axis with the hyperbola, was the vertex here, but it isn't the vertex here. This is like the two coordinate systems arguing about which point was the highest point. In any case, I know that t equal vx, and I know that x squared minus t squared equals 1. We should be able to figure out the coordinates of point Q. We should be able to figure out the coordinates of point Q in terms of unbarred values. according to the unbarred coordinates, point Q has x coordinate equals 1 over radical 1 minus v squared, and t coordinate v over radical 1 minus v squared. There's a great chance for some mass confusion here. The horizontal length, the space part, looks to be from x equals 0 all the way to x equals 1 over 1 minus v squared under the radical. This x number is bigger than 1, so horizontally from Q to the origin is bigger than 1. A long time ago, in one of the silly videos, I said that I could claim this to be the well-known Lorentz expansion, but I said that was just a joke. Do you remember what the resolution was? That end of the situation has t equals 0. That end of the situation does not have t equals 0. In the barred system, P and Q had the same t bar value, but P and Q do not have the same t value. This is the famous miss the bus problem. We measured one end at a certain time, t equals 0, and then we went off and had a coffee break or something, came back, the bus, having rolled down the street a little bit, has a larger end x coordinate, bigger than one would think. This expansion business is an illusion. It's going to turn out to be exactly the other way around, but we'll see that shortly. I've gone after this in this way, hopefully so that everybody will see that under reasonable Newtonian assumptions, plus the single assumption about this speed of light being constant, leads inevitably to this kind of stuff. There's going to be weird distortions in both time and space, and we're just going to have to get used to it. Coming up soon, we'll do a little bit of algebra-style work, the way that people usually think about this kind of thing. We'll do a little bit in the way of actual physics problems. We now have enough ammunition to do that. And then we're going to start talking about vector analysis and special relativity. After that, we talk about tensor analysis in special relativity, and then we make the jump to curved spacetimes. I've been sneaking up on these ideas so slowly that I hope it all seems fairly obvious to you by now. Until next time, I hope that everybody has a good day, and I'll talk to you again soon.